Aloha, everybody. This is Gigi from Kauai Community College. In this video, we are talking about related rates problems, and this is sort of an application of implicit differentiation. Okay, so let's see what I mean by related rates. So, um, the idea in these types of problems is that we are computing the rate of change of one quantity in terms of the rate of change of another. So if you visualize, say, a spherical balloon, for example, and then you are blowing air into this balloon, the volume is increasing and so is the radius, right? So what is easier to measure? I think in this case, you know how much air you're blowing in, so the volume, the rate of change of volume is can be measured easier than the rate of the radius, right? Anyhow, one of them is given and you are looking for the other. So the procedure is to go ahead and find an equation that relate the two variables here. In this case, volume of the sphere and in relation to its radius. And then you will use implicit differentiation to take the derivative of both sides, plug in the information, and solve for the missing rate. Okay, so that's the idea of related rates. Now, here is an example of that spherical balloon. Okay, so this problem said that the volume is increasing at a rate of 100 centimeter cube per second. So as soon as we know that, we are talking about volume of a sphere, and the equation of a volume of a sphere is V equals 4/3 pi r cubed. And that's the relationship between the two quantities, as I have introduced in terms of related rates, right? Now, we would go and look further as far as what the question is saying. It is saying that the rate at which the volume is increasing is 100 centimeter cube per second. So that is dV dt, the change in volume with respect to time. That's in seconds. Okay, so dV dt is 100. Now the question is asking you at the moment when the diameter is 50 centimeters, or we would say at the moment when the radius is 25, what is the rate at which the radius is increasing? Okay, in other words, what is dr dt when r is 25? Well, we are going to use implicit differentiation to take the derivative of both sides of that relationship there. And we will obtain dV dt is equal to, move the 3 down and that divide out with that 3. So we will have 4 pi r squared dr dt. Okay, so that right there is implicit differentiation. Okay, so that's something that we should have learned before this unit. Okay, so now we just plug in the information that we know. In other words, dV dt is 100, radius is 25, and we are looking for dr dt. When solving for dr dt, we will have dr dt equals 1 over 25 pi, and the unit would be centimeter per second because we're talking about the rate at which the radius is increasing with respect to time, right? You can get a decimal to see if it makes sense, and the decimal value would be roughly 0.0127 centimeter per second. I mean, to me, that makes sense in terms of the relationship between volume and radius. And I can visualize that as when the radius is already at 25 centimeters, if you keep blowing air into this balloon, the volume is increasing at 100 100 centimeter cube per second, and the radius is increasing at 0.0127 centimeter per second. That's what it's saying. Okay, so here is another problem. And we'll call this the ladder problem. This is number 2 in your note handout. The ladder that is 10 feet long is resting along against a vertical wall. Okay, so a ladder resting against a wall. And so what's going on with this ladder? As the bottom of the ladder is sliding out, okay, the bottom of the ladder is sliding out, then the top of the ladder is sliding down vertically, right? So we're talking about a horizontal distance and a vertical distance. With that said, I see a right triangle. And so let's call that horizontal distance, meaning the bottom, where the bottom of the ladder is to the wall. Let's call that X. And where the top of the ladder down to the ground is Y. And the hypotenuse being the ladder, and that would be 10 centimeter, and that's not going to change. What's changing is the horizontal distance and the vertical distance. So the relationship that we're looking at here is x squared plus y squared is equal to 100. That's the equation we're going to work with. Okay. Now, when we keep looking, we would see in the problem states that the dx dt, meaning the rate at which the bottom of the ladder is sliding away from the wall, that dx dt is 1 foot per second. The question is asking, at the moment where the bottom of the ladder is 6 foot away from the wall, what is the rate of the top of the ladder sliding down from the vertical wall there? Okay, so we're looking for dy dt when x is 6. But before we plug that information in, we are going to have to go ahead and take the derivative of both sides of that x squared plus y squared equals 100. Implicit differentiation applies, and we will have 2x dx dt plus 2y dy dt is equal to 0. The derivative of a constant is 0. Plug in the information that we know, where x is 6, x is 6, dx dt is 1. Okay, those are the information there. And y is 8. Okay, that red 8 right there is for you to ponder. Why 8? Where's the 8 coming from? Well, when x is 6, 6 squared plus y squared equals 100. 6 squared is 36. 100 minus 36 is 64. Square root of 64 is 8. So y is equal to 8. With that information, we will go ahead and solve for dy dx. 2 times 6 is 12. 2 times 8 is 16. Minus 12 divided by 16. Reduce. Dy dx is going to be negative 3 over 4 foot per second. So, as we are saying, when the bottom of the ladder is 6 foot from the wall, if this ladder continues to slide at 1 foot per second, then the top of the ladder would be sliding down at 3 feet every 4 seconds. That's what that answer means. Okay, that's the ladder problem. Next, we will do a very famous problem of this type, and that is the inverted cone problem. Okay, so imagine a water tank, and that water tank is in a shape of an inverted cone, meaning the cone is upside down there. Okay, now the radius is 2 centimeter and the height is 4 centimeters. Okay, so the shaded part there is denoting the fact that water is being pumped into it. And at some point, the water level is at the radius r and the height h. Okay, so those are our variables there. And we're talking about the fact that the water is being pumped into the tank at the rate of 2 meter cube per minute. That represents the volume, the rate at which the volume is changing. So we are talking about volume of a cone. Volume of a cone is 1/3 pi r square h. Now, in this equation, we have V, we have R, and we have H as our variable. Okay, now the thing that we know is dV dt. And then the question is asking the rate at which the water level is rising. So it's asking for dH dt when H is 3 meters deep. Nowhere in the information mentions the radius. So that is our clue to say, well, if the radius wasn't there, it would be great. I can just go ahead and take the derivative of both sides, and then I don't have to involve the radius and then dr dt, right? So let's go take a look. Let's go ahead and take a look at this part right here. Do you see two similar triangles? The small one and the big one. With the similar triangle, we would say R is to 2 is the same as H is to this whole entire long length, and that is 4. So R is to 2 is the same as H is to 4. Because within similar triangles, the lengths are correspondingly proportional. Okay, so multiply both sides by 2. R would be 2 divided by 4 is 2. So R is H over 2. We use that information and substitute in R for H over 2. Simplify, we will have volume is pi over 12 multiplied by H to the 3rd power. That's a simpler equation to work with because it only involves V and H, which is exactly what we would like to do. And what would we like to do? We would like to go ahead and take the derivative of both sides with respect to t. Implicit differentiation applies, and we will have dV dt is equal to 4 over pi over 4 h squared, right? Move the 3 down. 3 cancel with 3 and 12. 3 goes into both, and I have 4 left on the denominator. So that would be pi over 4 h squared dH dt. That's the implicit differentiation. We're solving for dH dt, so we have to plug in the information that we know. With dV dt being 2 and h is 3. Solving for dH dt, we have dH dt is equal to 8 over 9 pi, and the unit would be meter per minute. So the water is rising at the rate of 8 meters every 9 pi minutes when H has already gone up to 3 meters high. And that is it for related rates problems. Make sure you practice, do a lot of homework, and let me know if you have questions.